In the last video, we talked about some basics about electric circuits. We talked about current and voltage. We talked about the three common passive components, the resistor, the capacitor, and the inductor, and their IV or current voltage relations. For the capacitor, the current is proportional to the temporal rate of change of the voltage with the constant of proportionality given by the capacitance. So the temporal rate of change is expressed as a temporal derivative. If you have studied calculus before, you know what a derivative actually is, right? So for the inductor, the voltage is proportional to the temporal rate of change of the current with the constant of proportionality given by the inductance. So unlike the resistor, which is an energy dissipation device, both the capacitor and the inductor are energy storage devices. There is a concept that captures the characteristics of all three types of devices. It is known as the impedance, which is essentially the voltage divided by the current, the voltage across the component divided by the current. But before we can talk about the impedance, we need to have some basic understanding about complex numbers. I actually made a longer video about complex numbers before for a different sequence of videos, which is related to digital signal processing. You can access that video at this address. And the video that you are watching right now is basically a shorter version of that video. It's kind of a condensed version of that longer video. The longer video has some examples in it, but this one doesn't have any examples. So when we talk about a new numbering system, the first question is why do we need it, right? So why do we need to use complex numbers? Before we can answer this question, we need to understand a fundamental difference between math and physics. Physics usually describes natural laws that are imposed upon us by the universe. There's very little we can do about those natural laws. We can discover them, but there's very little we can do to actually change them. But math is actually something invented by human beings to make our lives easier. It is a language for describing the nature, and we can tailor it to our needs. The same is true about numbers. At the beginning of civilization, humans only had whole numbers, or natural numbers, which are just positive integers. Natural numbers allow us to carry out simple additions or summation. The sum of two natural numbers is still a natural number. So why do humans need negative integers, for example? Why do we need negative integers? Right? At the beginning of civilization, there's no negative integers at all. No negative integers. Right? The reason is because we need to carry out subtractions. When we subtract a large integer from a small integer, the result is no longer a natural number, and we need negative integers to actually represent the result of that subtraction operation, right? So, why do we need rational numbers? If we try to, for example, if we try to divide 5 pieces among like 3 people, right? If we want to divide like 5 pieces among 3 people, we need to do this kind of division. And the results may not be integers anymore, right? If you have 6 pieces divided by 3 people, then every people get like 2, right? But if you have like 5, then the result is not an integer anymore, right? So that's why we need rational numbers to represent the results of these kind of divisions, right? This kind of integer division. Then why do we need irrational numbers, right? Why do we need irrational numbers? Suppose we need to solve this kind of equation. In certain applications, we need to actually solve this kind of equations, right? And now we know that the solution is x equals to positive minus square root of 2. Right? And the square root of 2 can never be expressed as a division of 2 whole numbers or integers. You cannot do that. Right? People have proved that. Right? If you have any doubts, you can sort of look into the Wikipedia page about why square root of 2 is not a rational number. It's an irrational number. So we need irrational numbers to actually represent the solutions of these kind of equations. Right? The reason that we need complex numbers is no different from the reasons we need negative numbers, rational numbers, and irrational numbers. Complex numbers make our lives easier because if you follow a certain set of rules applied on the complex numbers, then this complex number system is both self-consistent, which means that those operations, the results of those operations are still complex numbers, right? That's what self-consistent actually means, and this complex number system can also provide very useful applications, among which is the study of electronic circuits. The discussion about complex numbers often starts with the number j. It is a letter, right? It's not really a number. But in the complex number system, we're calling this particular letter, j, as a number. It's actually a number. It's not a letter anymore. It's a number, right? And in some discipline, people use the letter I, right? But it's the same thing as j. Both letters actually refer to the same number in the complex number system, right? The reason that in electric engineering they are using j is because I has been reserved to represent the current most of the time. So people want to avoid this kind of confusion, so they use j, right? So if we try to solve this particular equation, x squared equals to 1, right? We know the solution is either positive or negative 1, right? But what about if we want to solve this particular equation? X squared equals to minus 1. Okay. If we're trying to solve this particular equation, then the solution, if it has a solution, right? If it has a solution, then this solution is definitely not inside of the real number space. It's not inside the real number. No real number can actually give you this particular solution to this particular, can give you a solution to this particular equation. It's impossible, right? So if we want to sort of have a solution, if we want to have something to represent the solution of this particular equation, then we cannot limit ourselves to just the real numbers. We have to extend our the set of all our numbers, right? So what we are doing is that we define something. We introduce a new definition, right? And this definition is j equals to the square root of minus 1. So that's sort of our definition. We use the letter j to represent the number, which is the square root of minus 1. Right? So if you are saying that the square root of minus 1 doesn't exist, right? True, it does not exist in the real number system, right? But if I define this number j as the solution of the square root of minus 1, then what's going to happen, right? What's going to happen? If I introduce this kind of definition, what's going to happen, right? The result is that it's going to open up the door to the complex number system, right? So everything actually starts with this particular definition. We have introduced a representation to the solution of the square root of minus 1, right? And this definition j is what we now call the imaginary unit. Right? J is now called the imaginary unit. It's a number now, right? It's a number now, and this number is called the imaginary unit. So if the square root of minus 1 equals to j, then the square of j must equal to minus 1, right? The square of j must equal to minus 1. And then what's going to be the cube of j, right? The cube of j equals to the square of j multiplied j. And the square of j equals minus 1. So minus 1 multiplied j is minus j, right? So j cubed actually equals to minus j. Then what's going to be the fourth power of j, right? The fourth power of j is j squared times j squared. So it's -1 times -1, it's equals to +1. So the fourth power j actually equals to 1, right? So 1 has another representation now in the complex number system, which is the fourth power of j of the imaginary unit, right? So by using those kind of relations, we can find an arbitrary positive integer power of j, say 1003 or something, right? So all you have to do is to factor 1003, factor this thing into like a factor of 4, right? So 1000 is like 4 times 250, right? And then multiply j to the cube. So j to the fourth power is 1. So 1 to the 250th power is still 1. So 1 times j to the third power, that's minus j, right? J minus j, right? The negative powers of j, right? For example, if you want the -1 power of j, you can do it by using a division. So 1 divided j. Right? 1 is j to the fourth power. So it's j to the fourth power divided by j. Then it's j to the third power. J to the third power is minus j. You got that already, right? And then what's actually the j to the -2 power? Then it's 1 divided by j to the second power. Right, it's 1 divided by -1, and then it's -1. So for any kind of arbitrary negative power of j, you can also obtain the solution. Later on, after we have talked about the Eulers form or Euler's equations, we will see that multiplication by j is equivalent to clockwise rotation in the complex plane by 90 degrees, and division by j is equivalent to counterclockwise rotation by 90 degrees. So any power of j can be actually represented as multiplications of j multiple times. So in the complex plane, it's just the rotations, either clockwise or counterclockwise, depending upon you are doing a multiplication or division, 90 degrees multiple times, or clockwise or counterclockwise, 90 degrees multiple times, right? Once we have a definition of the imaginary unit, we can define a two-dimensional plane with the horizontal axis given by the real number, given by the real axis. So all the real numbers, 1, 2, 3, all the natural numbers, rational numbers, irrational numbers, all the real numbers are going to live on this horizontal axis, and it's denoted as RE here, real, right? And then the vertical axis looks like it's perpendicular to the real axis, right? Right, it's perpendicular to the real axis, and then the unit length on this imaginary axis or IM axis is exactly the imaginary unit j. So a unit length on this vertical axis is j, right? And the standard form of a complex number has two components. The real part, a here, right, and then the imaginary part, which is b here, right? The entire complex number a plus bj is just you can actually think of it as a point on this two-dimensional plane. So the horizontal axis is given by a here, and then the vertical axis is given by b here. So a plus bj is just like a vector with its horizontal axis given by a, right? And then its vertical axis given by b. The j is just the unit direction, the unit vector on the vertical direction, right? That's what j actually looks like, right? So so every complex number in the standard form actually corresponds to one point on the two-dimensional complex plane, right? And its horizontal and the vertical axis coordinates, horizontal and the vertical coordinates are given by the real part and the imaginary part, respectively. Right. Then what's going to be the addition and subtraction of two complex numbers? For example, we have two complex numbers. One is a plus bj, and the other one is c plus dj. Right? We have like two different complex numbers. Not two different complex. We're interested in getting the addition of these two complex numbers and the subtraction of these two complex numbers. Right? It's actually quite straightforward. So the result for addition is that we're just adding the real parts together. So a plus c, we're just adding the two real parts together. And then that's going to be the real part of the result. Right? And then we add the imaginary parts together, b plus d. And that's going to be the imaginary part of the result. For subtraction, it's the same thing. Just subtract the real part. That gives you the real part of the result. And then subtract the imaginary part. That gives you the imaginary part of the result. Right? So addition and subtraction can be carried out without too much of a difficulty. Right? Multiplication. Right? The multiplication is slightly more complicated. It actually follows the rule of polynomial multiplication. Right? So how do you actually do polynomial multiplication? Right? So it's a plus bj multiplies c plus dj. That's the one complex number. That's the other complex number, right? How do you actually multiply them together? You do polynomial multiplication. So a multiplies c, so ac give you here, right? And then a multiplies dj, so a dj. You add them together because this is a positive sign, right? And then this term and this term, so bcj. And then this term and this term, so positive bj times positive dj, so it's bdj squared. Right? Don't forget, j squared is what? J squared is minus 1. So it's ac, subtract bd. These two terms don't have j in it. Right? These two terms. So it's ac subtract bd. That's the real part of the result of the multiplication. Right? And then adj plus bcj, both terms have j in them. Right? So you collect the j. You get ad plus bc, and then take the j out. Right? So that's the imaginary part of the multiplication result. Right? That's how multiplication is done. Basically, it's just a polynomial multiplication. And you have to take into account that the square of j equals to minus 1. And then the rest of them are just some kind of algebra. Right? The division is slightly more complicated than multiplication. We can do divisions of complex numbers by following these 3 steps. Right? So the first step is to find the conjugate of the denominator. What exactly is the conjugate, right? So if you have a complex number that's a plus bj, that's your complex number. Then the conjugate of that complex number is a subtract bj. Right? That's called a conjugate of a complex number. You just reverse the sign in front of the imaginary part. That gives you the conjugate. Right? And then that's the first step, right? The second step is to multiply both the numerator and the denominator by the conjugate of the denominator. That's the second step. And then suppose the denominator is a plus bj, right? And then its conjugate is a subtract bj. If you are multiplying this conjugate to both the numerator and the denominator, let's just look at the result on the denominator, right? So it's a subtract bj times a plus bj. We again do polynomial multiplication, right? Polynomial multiplication, what we get is a squared, right? A squared. Then a times positive bj, then it's a bj. Right? And then minus bj times a, then it's minus a bj. So minus a bj and the positive a bj cancels out. Right? And then minus bj times positive bj. Then it's minus b squared j squared. That's minus b squared j squared, right? Don't forget j squared is minus 1. Right? So it becomes a squared plus b squared. Right? So the denominator, after multiplying the conjugate, the denominator is going to become like that. Right? So and then the third step is just to simplify the expression and then collect all the real and imaginary parts. Right? Collect all the terms that belongs to those real and imaginary parts. So let's look at the example. We have like 2 complex numbers. One is c plus dj, and then the other one is a plus bj. We are dividing them. Right? So the first step is to find the conjugate of the denominator, which is a subtract bj, right? And then the second step is to multiply a subtract bj to both the numerator and the denominator, right? So if you multiply the conjugate to the denominator, that's what we have done already. It's a squared plus b squared, right? And then if you multiply these two complex numbers together, what's going to be the result, right? Again, polynomial multiplication. So it's a times c, right? And then minus bj times positive dj. So it's minus bdj squared, right? And then a times dj, that's a dj. And then minus bj times c, so it's minus bcj, right? J squared is minus 1, so it becomes ac plus bd. And then these two terms we can collect the j out of the subtraction, so it's ad subtract bcj, right? And then we can just sort of collect all the terms belong to the real part and collect all the terms belong to the imaginary part. In this case, all we have to do is to sort of separate these two summation and the division. So it's ac plus bd divided by a squared plus b squared. That's the real part. And then the imaginary part is given by the other half, basically. Right? So that's how we do divisions of complex numbers. Right? After we are more comfortable about the standard form of complex numbers, let's look at the polar form of complex numbers. Right, what the polar form actually is. So because every complex number corresponds to a point on the two-dimensional complex plane, so we can determine its location by not just its coordinates on the horizontal and vertical axis, but by its distance to the origin, which is r here, right? And then its angle with respect to the positive real axis alpha, right? So if we fix the distance and then also fix the angle alpha, we can determine that point uniquely, right? And this coordinate using r and alpha, which is represented using this kind of sort of symbol, right? R is the distance, right? Distance to origin, and then this triangle is called alpha. It's called the angle. It's angle alpha, right? This representation is a polar representation. It tells you the distance to origin and then the angle with respect to the positive real axis, right? And this is called the polar representation. And the polar representation can be converted to and from the standard form without too much of a difficulty. So suppose you are given the polar representation r and alpha, right? You can get the real part by just doing trigonometry. So the distance here is r, right? The angle here is alpha. What you want to get is the projection onto the real axis, right? This is the right angle, 90-degree right angle, right? So the length of this side is what? It's r times cosine alpha. So a equals to r times cosine alpha, right? And then how do we actually get b? B is the vertical, the length on this side. That's this side, right? So that's r times sine alpha. You get this length. Right? So this way you get the real and imaginary parts. Right? If you assemble them together, a plus bj equals to what? Equals to r times the whole thing in the square bracket. The whole thing in the square bracket is exactly cosine alpha plus j sine alpha. The stuff in the square bracket is actually a vector with the length of unit, with the length of 1, right? And then with the angle of alpha. Right? You're basically just scaling this unit length vector by a length r, right? And this unit length vector has an angle of alpha with respect to the real axis. So that's going from the polar form to the standard form, right? So how do you actually go the other way around? How do you actually convert from the standard form to the polar form? It's also relatively easy. It's not too complicated. So if you are given a and b, you know a and b, then what's going to be the length of r, right? Don't forget this is a right angle. It's a 90-degree right angle. So the length of r equals to the square root of a squared plus b squared, right? And in the US, they call this thing Pythagorean theorem. That's the Pythagorean theorem. It's the Pythagorean theorem. In China, they use a different different person's name. I think. So it's called an entirely different thing, basically. So, that's sort of the distance to the origin, right? That's r, and you are still missing arva. How do you actually get the arva? Right? We know the tangent arva. Tangent arva equals to what? The tangent arva equals to b divided by a. Right? Tangent arva equals to b divided by a. So arva is the arctangent, the inverse of the tangent, b divided by a. But it's not that simple. It's not really that simple. Depends upon the sign of a and b, right? So you have to sort of pay attention to the sign of a and b, right? And then decide what kind of formula you're going to use. So if a is larger than 0, then it's just arctangent b divided by a, right? But if a is smaller than 0, but b is larger than or equal to 0, you have to add pi to it. You have to add 180 degrees to it, to the result of the arctangent, right? But if a is smaller than 0 and b is smaller than 0, then it means the angle is actually in this quadrant, right? And then you have to subtract pi from the arctangent. The reason that you have to do this kind of thing is because when you do the b divided by a, the sign information is lost, right? You have no idea which one is positive, which one is negative, right? Once you have done a division. So that's why you have to sort of, and the sign actually is important, you know, because depending upon the sign of a or b, it may live in different quadrant, right? So that's why you have to sort of separate the different cases and then add pi or subtract pi to it. And then you have to worry about a when a equals to 0. If a actually equals to 0, which means that the real part is 0, so the complex number is entirely an imaginary number, lives on this vertical axis, right? So alpha is either pi over 2 or minus pi over 2, depending upon b is positive or negative, right? So when both a and b are 0, then which means it's just the 0 complex number. In this case, alpha is indeterminate. Right? You cannot really determine what r is. It can be anything, right? But in that case, it doesn't really matter what r actually is, right? Because you have a 0 vector. The length is 0. It doesn't really matter what the angle actually is, right? One important thing to keep in mind is that the angle obtained from this particular formula is not really unique, right? Because if you add an integral multiples of 2 pi to the alpha obtained from this formula, the vector is still in the same direction, right? So alpha plus 2 pi multiply 2, alpha plus 2 pi multiply minus 2, or any integer, still gives you the exact same direction. So in this case, alpha is not really unique, right? But it doesn't really matter. All we have to worry about is to take the alpha that's within a certain range. For example, minus pi to pi, or 0 to 2 pi, that kind of thing, which will give you equivalent results. So that's the polar form, right? And the form that's used most often is the so-called Eulers form, right? The Eulers form is the one that we must remember and must know how to use. Right? And what exactly is the Eulers form, right? What exactly is the Eulers form? Here we have looked at the sine alpha and the cosine alpha. In the polar form, we have sine alpha and the cosine alpha, right? Suppose we expand the sine alpha and cosine alpha in Taylor series. Then what we are going to get is this kind of expression. So for sine alpha, it's alpha subtract 3 factorial alpha to the cube divided by 3 factorial plus alpha to the 5th power divided by 5 factorial subtract, that kind of thing. So you can get the Taylor series by using either Mathematica or by consulting with any kind of a calculus book, or just by Googling. You can get the Taylor expansion of sine alpha. That's not really too complicated. You can do the same thing for cosine alpha, Taylor expansion for cosine alpha. Then it's going to look like that, right? That's a Taylor expansion for cosine alpha. And then you can try to do the Taylor expansion of this exponential, it looks very strange exponential, right? It's e to a power of something, but this power of something is actually an imaginary number, right? It's alpha times j. J is our imaginary unit, right? So it's an imaginary power of j, of e, basically, right? We know what's actually the real power of e, right? E to the first power, e to the second power. That's kind of thing that we are familiar with. But e to the j omega, j alpha's power, right? That's something that we are not really familiar with, right? But it's okay. It's okay. We can still do the Taylor expansion of e to the anything's power, right? Suppose you replace j alpha with a symbol x, right? Then what's going to be the Taylor expansion of e to the x power? Right? It's going to be 1 plus x, right? And then plus x squared divided by 2, and then go on like that, right? And then after we got the Taylor expansion, we replace x with j alpha again. Right? Then we're going to get the Taylor expansion of e to the j alpha. And the Taylor expansion of e to the j alpha is going to look like that, with the infinite number of terms, basically. Right? And then we can try to collect all the real parts and all the imaginary parts. So here is the one real part, right? Another real part, right? Another real part, and then here it's one imaginary part. That's one term in the imaginary part. Another term in the imaginary part. Another term in the imaginary part. So all we have to do is to collect them. So collect them for the real part. You collect all the terms, and then for the imaginary part, you collect all the terms, right? Collect all the j outside of the parentheses, right? And then you immediately discover that all the stuff that's inside of the real part is actually identical to the Taylor expansion of cosine alpha. And then all the stuff that's inside of the imaginary part is identical to the Taylor expansion of sine alpha. Right? Here I just listed the first 3 terms, right? But if you are interested, you can sort of use Mathematica to actually get lots more terms, 100 terms, 200 terms, that kind of thing. And then you can compare what I'm saying is actually true, right? So it means what? It means e to the j alpha's power actually equals to what? The real part is actually cosine alpha, and then the imaginary part is actually sine alpha. So e to the j alpha's power equals to cosine alpha plus j sine alpha. That's the Eulers equation. It's extremely important. Right? It's extremely important. So for any kind of a standard form a plus bj, we can obtain the polar form, right? The polar form, which is equal to r times cosine alpha plus j sine alpha, right? Now we know that cosine alpha plus j sine alpha actually equals to e to the j alpha's power. So now we can actually replace everything inside the square bracket with just this exponential, right? So any complex number now have a Eulers form, which is r, the distance to origin, times this complex exponential e to the j alpha power. Right? That's this red symbol here. So the standard form represented using 2 coordinates. The polar form represented using the distance and alpha. And the Eulers form r times the complex exponential e to the j alpha's power, all refer to the same complex number, the same point on the 2-dimensional complex plane. Right? So the Eulers form is very convenient. It's actually very convenient. So suppose we have the Eulers form for this particular complex number a plus bj. Now we have its Eulers form, and it equals to r times e to the j alpha's power. Right? That's the Eulers form for this particular complex number. Right? Then what's going to be the square root of that complex number? Right? We haven't talked about the square root of a complex number. We talked about addition, subtraction, multiplication, division. Right? We haven't talked about taking the power of 1/2. So how are we going to do that? Right? How are we going to do that? If we are just doing 1/2 power of a plus bj, it's kind of confusing, right? We don't really know how to do that. But if we are applying 1/2 power on r times e to the j alpha power, that's something we know how to do, right? It's just two numbers multiplying each other, and then the whole thing is raised by 1/2 power. So all we have to do is to apply this power to each term. So r gets 1/2 power, and then multiply e to the j alpha gets 1/2 power, right? And that gives you j alpha divided by 2. So now you can see how do you actually get the square root of any complex number, right? All you have to do is to take the square root of the distance to origin. Take the square root of that, and then divide the angle with respect to the positive real axis by half, right? And then that vector or that point is the result of taking the square root. So you can actually take the square root in a graphical way, right, by doing that. And the same kind of thinking can be generalized to any kind of power. It doesn't have to be square root, right? It can be anything. Positive or negative, doesn't matter, right? So once you have the Eulers form, taking power becomes really easy, right? So now let's look at the multiplication and division again. So suppose you have another complex number, c plus dj, and it's got its own Eulers form, which is capital A times e to the j theta's power. That's it. That's the Eulers form for this complex number, right? And then what's going to be the multiplication, right? So it's r e to the j alpha. That's a plus bj, right? And then times a times e to the j theta. That's the complex number that's the Eulers form for c plus dj, right? And then all you have to do is to multiply the distance together. So r times capital A. And then e to the j alpha times e to the j theta equals to e to the j alpha plus j theta, right? And then you can collect the j out of the factor j out. It becomes e to the j alpha plus theta, right? So graphically, how it's going to happen, right? What's going to be the operation that we're going to apply? Suppose we are looking at the operations we're going to apply on this particular complex number or this vector, right? And this vector is the operations we are going to apply, and this is the operator. This is the vector we are trying to transform. Then what's going to happen, right? What's the operations we are going to apply? The first thing we are going to apply is to scale r by a factor of a, right? R times a. So if a is like 100, then we want to sort of scale r by a factor of 100 to increase r for like 100r, that kind of thing, right? That's the first thing we want to do. And then the resulting vector must be rotated counterclockwise by an angle theta. Suppose theta is a positive angle, right? Say 10 degrees or something, right? Right. So after the scaling of the distance, what we are obtaining is r times a e to the j alpha, right? After the rotation, without changing the distance, after the rotation by theta, we obtain r times a e to the j alpha plus theta, right? So multiplication becomes a scaling of the distance combined with a rotation counterclockwise if the theta angle is positive, right? If theta angle is negative, you just rotate the clockwise, right? If it's positive, you rotate the counterclockwise, but if it's negative, you rotate the clockwise, right? So multiplication can be done in this particular way. And then what about division, right? What about division? The result of division is just like that, right? Again, you have to scale the radius, the distance r, but by the inverse of a instead of a, right? And then the angle here, it's not plus theta anymore. It's subtract theta. So it means that if theta is actually positive, you have to rotate clockwise, and if theta is actually negative, you have to rotate counterclockwise, right? So division becomes a scaling of the distance combined with a clockwise rotation, right? So that's how we can actually think of complex number multiplications and complex number divisions, right, in the Eulers form. And there are two special situations we have to sort of pay attention to. If the distance to origin is unity, r is 1, and the angle is 180 degrees. On 180 degrees, that's exactly pi, right? From the positive real axis, 180 degrees. Right. Then the complex number is e to the j pi, right? And then the complex number actually corresponding to -1 on the real axis. Right, so e to the j pi equals to -1. Right. So multiplying by -1 is actually equivalent to rotating counterclockwise by an angle of pi, or 180 degrees. Right. So every time if you multiply by -1, it's equivalent in the complex plane. It's equivalent to rotating 180 degrees counterclockwise. Right. And then if again the distance to origin is again unity, right? But now the angle alpha equals to pi over 2. It's 90 degrees. Then where the complex number is gonna be, right? It's gonna be here. It's gonna be here. And this location is actually the imaginary unit j, right? Because the length is 1, and j is the unit vector on the vertical axis, right? So every time if you multiply j, it's equivalent to rotating by 90 degrees on the complex plane. And then if you divide by j, it's equivalent to rotate clockwise by j, by 90 degrees. Right? So multiply by -1 is equivalent to multiplying j twice. Right? Multiplying j once rotates 90 degrees. Right? Multiply another j, you rotate the counterclockwise by another 90 degrees. That gives you 180 degrees, right? And j squared exactly equals to -1, right? So -1 equals to j squared, right? J squared means rotate counterclockwise by 90 degrees twice, right? That's j squared actually means. So j squared actually equals to -1. That's sort of the geometrical interpretation of the definition of the imaginary unit. So we have talked about alternating current. Right? The voltage as a function of time is a sine or cosine function. And in the US, the majority of the AC sources have a frequency of 60 Hertz. And in everywhere else in the world, AC power usually has a frequency of 50 Hertz. Right? That's sort of the AC power. They look like sine or cosine waves. They are actually sine or cosine waves, actually. The reason that we are studying Eulers form of complex numbers is that sine and cosine functions can be expressed using the Eulers form. Right? So e to the j alpha equals to cosine alpha plus j sine alpha, right? What about e to the minus j alpha? Right? It equals to cosine minus alpha plus j sine minus alpha. Right? Cosine function is an even function, so cosine minus alpha equals to exactly cosine alpha. Right? But the sine function is an odd function, so sine minus alpha actually equals to minus sine alpha. So e to the minus j alpha actually equals to cosine alpha subtract j sine alpha. Right? That's Euler's equation. So how do we actually express cosine alpha and sine alpha using these two complex exponentials, right? So all we have to do is to add these two equations together. So positive j sine alpha minus j sine alpha cancels out. What you're having is 2 times cosine alpha, and then e to the j alpha plus e to the minus j alpha. And then all you have to do is to divide 2 on both sides. Then cosine alpha equals to 1/2. These two add together. Right. If you want to get an expression for sine alpha, all you have to do is to subtract these two equations. So cosine alpha cancels out. Right. These two complex exponentials subtract each other and then divide by 2j. Right. So alpha is an angle, right? Angle. But now let's replace alpha with omega t. And t is time. Omega is sort of the angular speed. So how fast you are actually rotating. So angular speed times time multiplying time equals to the angle that you have rotated through. Right? So cosine omega t. Then if we replace alpha with omega t, then all we have to do is to replace alpha here with omega t, alpha here with omega t. So cosine omega t actually equals to 1/2 e to the j omega t plus e to the minus j omega t. Right? You can do the same thing for the sine omega t. You get the same thing. Right? And the cosine omega t and the sine omega t can actually be used to represent those voltages, those alternating current voltages and currents. Right? So you can actually represent those cosine and sines using those complex exponentials now. Right? And then what's going to be the advantage of using those complex exponentials? Right? We talked about the derivative. We talked about the derivative with respect to time, right? But let's look at the derivative with respect to alpha first, right? So the derivative of e to the j alpha with respect to alpha is exactly j times e to the j alpha. Right? So the rule for taking derivatives is identical to the to ordinary exponentials, basically. Right? This is a complex exponential because it has j in it. Right? But the rule for taking derivatives is actually exactly the same as the rule for taking derivatives of an ordinary exponential. J is just a coefficient in front of the stuff that you are trying to take derivative to. Right? And now if you sort of replace alpha with omega t and take a derivative with respect to time t, the rule of differentiation still applies, right? So it's j omega, the stuff in front of t, basically. You're taking a derivative with respect to t. So it's a Chan's rule, right? Chan's rule. So first take a derivative of e to the j omega with j omega with respect to j omega t. Then that gives you e to the j omega t. Right? And then take a derivative of j omega t with respect to t. That gives you j omega. Right? So the derivative of this complex exponential is still the same complex exponential, exactly the same, without any change, right? Multiplying j omega. Multiplying with omega is easy because it's just a real number, which just means change the length of your complex number by omega, by a factor of omega, right? J means what? Multiplying by j means rotation of 90 degrees counterclockwise, right? So this complex vector, this complex number can be easily obtained. So derivatives has been replaced with just a simple multiplication and a rotation, right? It's a much simpler sort of operation. Right? But if you are using cosine or sine signals, you have two terms, right? It's not just the e to the j omega. You also have e to the minus j omega. What about the temporal derivative of e to the minus j omega? Right? It equals to minus j omega e to the minus j omega t. And if you are interested, you can check this complex number is actually the conjugate of this complex number. Right? So effectively, you don't really have to take a derivative. All you have to do is to actually conjugate this one. Conjugation is really, really easy, right? All you have to do is to flip the sign on the imaginary part. Right? It's a very, very easy operation. So once you conjugate this term, then you are obtaining the derivative that's applied on the second term. So you don't really have to take a derivative. All you have to do is to conjugate the derivative that they have already taken. Right? So in practice, even though you have introduced like two different terms to represent a single cosine, it doesn't mean you have twice as much work. In fact, the amount of work is actually reduced by a significant amount because it's very easy to take derivatives on a complex exponential. Right? And then the other term, the result from the other term can be easily obtained by just conjugating the result you have obtained for the first term. Right? And then you just add them together. The rule of superposition also applies. Add them together, you get the result for a cosine input or sine input. Right? So by using those complex exponentials, we can simplify our calculations substantially.